Hello everyone, my name is Vatsal Shah and today I'm going to be demonstrating the implementation of the RSA algorithm in Python. Before we get into the coding part, I want to explain what cryptography is all about. Cryptography is the process of transforming plain text into ciphertext to ensure the security of communication. It involves the use of codes and ciphers to convert messages into a form that cannot be understood by unauthorized individuals. This technique is used widely in various fields, industries including banking, emailing, e-commerce, and others to ensure the confidentiality and integrity of data during its transmission. Asymmetric encryption, also known as public key cryptography, employs two distinct keys for encryption and decryption. One of these keys is public, whilst the other is private. The public key is used to encrypt the data and the private is used to decode the data. Imagine that you want to send a secret message to your best friend, but you don't want anyone else to read it. You could write the message in a secret code. However, if someone else found out the code, they could easily read the message. This is where encryption comes into play. You decide to use a special machine to encrypt your message. This machine uses a special or complex algorithm that transforms your message into a mixed up mess of letters and numbers which nobody can understand. To make sure that only your friend can read this message, you give them a special key that can unlock the encryption and reveal the original message. To send the message, you type it into the machine and it delivers the encrypted version. You then send the encrypted message to your friend through a secure channel, like a courier or a locked mailbox. Once your friend receives the message, they use their key to unlock the encryption and reveal the original message. This process ensures that nobody else can read your message even if they intercept it during transmission. It also includes that only the intended recipient, your friend in this case, can decode and read the message during using their key. This is similar to how encryption works in the digital world, where messages are encrypted using algorithms and keys and sent over secure communication channels to ensure that only the intended recipient can read them. Asymmetric information involves three key steps. Firstly, a user generates a pair of keys, a public key and a private key. The public key is shared freely with anyone who wants to send a message to the user, whilst the private key is kept secret. Secondly, the sender encrypts their message using the recipient's public key. This ensures that only the recipient who holds the corresponding private key can decrypt and read the original message. Finally, the recipient uses their private key to decrypt the message that was encrypted using their public key. This ensures that only the intended recipient can read the original message, providing a secure and private communication channel. Now we will be going over the flowchart for this algorithm. First, we select two large prime numbers P and Q. This is because the security of the RSA encryption scheme is based on the difficulty of factoring large prime numbers into their prime factors. When two large prime numbers are multiplied together, the result is a number that is very difficult to factor into its component primes. This is especially true if the prime numbers are large enough, and the larger the prime numbers, the more difficult it is to factor the resulting number. Then we store the product of p minus 1 whole and q minus 1 whole under the variable phi n, where n was defined in the previous step. Next, a value of e is chosen such that it is greater than 1 and less than phi n, and the greatest common divisor of phi n and e is 1. The reason for choosing such an e value is to ensure that it is relatively prime with phi n. It also ensures that there is no efficient algorithm to find the value of d, the private key component, that satisfies the equation E multiplied by D equals to 1 mod of phi n, and this is known as the RSA problem, which is the basis of RSA encryption. I'm now going to go over the mathematical calculations and the proofs behind the RSA algorithm, and I'm also going to be writing the key equations which is going to be used also in the code following in this video. RSA encryption is based on the difficulty of factorizing large composite numbers into their prime factors. In this algorithm, two large prime numbers p and q are chosen and the product n is equal to pq is used as the modulus. Two additional values e and d are chosen such that ed is equal to 1 mod p minus 1 times q minus 1, and e is the encryption exponent while d is the decryption exponent. The public key is n, e, while the private key is d. To encrypt the message m, we compute c is equal to me mod n. To decrypt this ciphertext c, we want to show that m is equal to cd mod n. To prove this, we first need to define the function phi n, which represents the number of integers less than n that are relatively prime with n. If n has prime factors p1, p2 all the way to pr, and k1, k2 all the way to kr is the respective powers, then phi n can be calculated as n bracket 1 minus 1 over p1 bracket closed bracket open 1 minus 1 over p2 bracket closed all the way till 1 minus 1 over pr. For the RSA modulus n equal to pq, we have phi n is equal to p minus 1 whole times q minus 1. Additionally, we can use Fermat's little theorem in the form of Euler's theorem, which states that if x is relatively prime to n, then x phi n is equal to 1 mod n. Returning to our decryption process, we start with the equation med is equal to m bracket ed minus 1 plus 1, which is equal to m times m k prime bracket close n mod n. This is derived by substituting ed equal to 1 mod p minus 1 times q minus 1 into the equation for cd and raising both sides to the d power. Next, we use Fermat's little theorem to simplify the equation to med equal to m bracket close mk phi n is equal to m mod n, which is equal to m. This implies that raising the ciphertext c to the power d and reducing it to modulo n will recover the original message m. Overall, RSA encryption and decryption rely on the mathematical principles of prime numbers, modular arithmetic, and the Euler's theorem to securely transmit information over insecure channels. Now we will dive into the actual program by using real numbers to illustrate this algorithm. First, we import the math library to perform the necessary modular arithmetic calculations in the RSA algorithm. Next, we assign the values of two prime numbers p and q to be 3 and 7 respectively. These values are chosen randomly, but they need to be kept secret as they are from part of the private key. The product of p and q is then computed and stored in the variable n. This product forms part of both the public and private keys. The next step involves computing the value of phi n using the formula p minus 1 whole times q minus 1 whole. This value is indeed needed to find the encryption and decryption exponents e and d. To ensure that p and q are indeed prime numbers, Fermat's little theorem is used. This theorem states that if p is a prime number and p does not divide x, then x to the power p minus 1 is equal to 1 mod p. In the code above, Fermat's little theorem is not explicitly used, but it is a part of the underlying math that makes RSA secure. To find a suitable value of e that satisfies the greatest common denominator between phi n and e to be equal to 1, we use Euler's theorem. This theorem states that if x is relatively prime to m, then x to the power phi n is equal to 1 mod n. In other words, if the greatest common divisor between x and n is equal to 1, then x raised to the power of phi n is congruent to 1 modulo n. Using this theorem, we loop through values of e greater than 1 and less than phi n, checking if the greatest common denominator or greatest common divisor of phi n and e is equal to 1. If the condition is satisfied, we break out of the loop and increment the value of e by 1. After computing the value of e, we print it to the screen and assign the value of k to be 2. This value is used to compute the decryption exponent d. To compute the decryption exponent d, we use the formula d is equal to k phi n plus 1 whole divided by e. This formula follows from the fact that ed is congruent to 1 modulo p minus 1 whole times q minus 1 whole, which implies that there exists an integer k such that ed is equal to k phi n plus 1. Rearranging this formula, we get d is equal to k phi n plus 1 whole over e. Once we have computed the encryption and decryption exponents E and D, we print out the public and private keys as tuples of the form E, E, N, and D, N, respectively. The plain text message that we want to encrypt is assigned to the variable MSG, short form of message, which is set to 11 in this example. To encrypt the plain text message, we use the formula C is equal to m to the power E mod n. In the code above, we use the pow function to compute m to the power E and then use the math.f mod function to compute the modulus of the result with n. To decrypt the ciphertext message, we use the formula m is equal to c to the power d mod n. In the code above, we use the pow function to compute c to the power d and then again use the math.f mod function to compute the modulus of the result with n. Finally, we print out the original message, the encrypted message, and the decrypted message to verify that the encryption and decryption processes are working correctly.